Hello, my name is Stephen Calciano, and I'm a Senior Product Manager for Chemistries and Consumables at Waters Corporation. I'm excited to present the next module in our Peptide and Protein Bioanalysis Bootcamp series, developing an automated platform for standardized large molecule bioanalysis sample preparation. Let's get started. The goals of this presentation are to understand the drivers of wanting to automate sample preparation for large molecule bioanalysis. We want to also evaluate areas in the workflow that would benefit from implementing automation, and then explore automation method development with a focus on affinity purification, digestion, and solid phase extraction. There are a number of macro industry trends driving automation in bioanalysis today. The large molecule drug discovery and development pipeline is growing rapidly, with an increasing number of preclinical studies. This has been accompanied by an increase in the complexity of modalities entering this pipeline. So sophisticated LC-MS sample preparation methods have emerged for quantification of proteins. For example, the hybrid immunoaffinity LC-MS assay. So there's a need for reproducibility, repeatability, and transferability of these assays to cover all the sources of potential variability. The benefits of automated sample preparation are numerous. As we see an increasing number of samples and projects come through, automation can help us eliminate the bottlenecks associated with sample preparation. This is reflected in the increasing complexity of the biologics and the intricate sample preparation workflows which are required for LC-MS. So leveraging automation for liquid handling can enable us to streamline these complex workflows like affinity sample preparation and digestion. Additionally, as we look to address reproducibility, repeatability, and transferability, automation can help eliminate some of the variables associated with implementing these methods and ultimately transferring these methods from site to site. Sample preparation automation is generally perceived as having many barriers to adoption. There are requirements for pretty major capital investments in this technology. Additionally, there is a level of technical expertise which is required to deploy automation effectively. There's always the question of comparability of data to your manual assays, and there's a time and expertise associated to develop scripts to run automation that can't be overlooked. Even with those challenges, the benefits to implementing automation are numerous. We can increase capacity and throughput, ultimately increasing the efficiency of our labs. Additionally, we can reduce human errors and eliminate repetitive tasks, all the while ensuring assay reproducibility. All of these are extremely valuable capabilities that can provide long-term organizational benefit. Now that we've reviewed industry drivers toward automation, as well as challenges and benefits associated with the technology, let's take a look at a specific example of automation in the context of a protein bioanalysis workflow. In the next section of this presentation, we will highlight areas in the workflow where sample preparation can be automated for protein quantification using the Surrogate Peptide Approach. Here we outline a typical surrogate peptide analysis workflow. It begins by identifying unique peptides that will be used as a surrogate to quantify our protein. Then we optimize and fine-tune MS conditions for those surrogate peptides. Then goes on to our sample preparation method development, where we can perform optionally protein level cleanup, protein digestion, and peptide level cleanup prior to our LC-MS analysis. Then we perform data processing followed by reporting. Diving deeper into the surrogate peptide sample preparation workflow, we can see that the options associated with protein level cleanup, protein digestion, and peptide level cleanup for reagents and device formats are overwhelming. It's important to establish robust baseline criteria for our method because when we go to port our manual workflow to our automation, we want to make sure that we don't encounter any unanticipated variability. Establishing a robust sample preparation method manually is the first step in your automation journey. For this, we will use the Waters ProteinWorks method, generically outlined here. The ProteinWorks method applies a sequential denaturation, reduction, and alkylation pretreatment before enzymatic digestion. This pretreatment can improve the digestion efficiency by unfolding the proteins and increasing the accessibility of the digestion enzyme to the cleavage sites. These standardized workflows provide a great approach to sample preparation automation. Since the variables of reagent concentration, enzyme to substrate ratio and incubation time are pre-optimized, it eliminates the need for method development. It also provides a well-defined starting point for both purified and non-purified plasma samples. To create a benchmark for automation, we assessed assay performance of the ProteinWorks method when performed manually. Looking at the data from multiple surrogate peptides of Avastin, we observe low single-digit CV values for both inter- and intra-kit reproducibility. This translates to a reliable, robust, large molecule sample preparation workflow that is easy to implement. Now it will be up to us to recreate this type of performance with our automation workflow. In the next section of this presentation, we will explore an approach to automation method development in search of a broadly applicable sample preparation platform for large molecule bioanalysis. With any new project, it's important to identify success criteria at the outset. This platform has to be robust, and the data generated from automation has to be comparable to the manual method in terms of both accuracy and precision. Additionally, the reagents on deck need to be stable for the lifetime of the method. The platform has to be easy to use and flexible and accommodate non-programmers, and it has to be able to process a range of sample numbers. Additionally, we need to eliminate the need for any manual intervention while each of the sub-steps of the method are going on. This allows us to reclaim time to spend on other high-value tasks. Now that we have our benchmark method, we need to define our automation capabilities. When deciding how to set up the liquid handling system for automation sample prep, there are two main categories to consider: on-deck accessories and labware. We need to ensure we have the right on-deck accessories to perform the required heating, mixing, capture, and dispensing operations outlined in the ProteinWorks method. Additionally, compatible labware must be chosen to successfully execute the method and achieve the expected result from our manual protocol. A summary of the manual to automation method changes is captured here. First was a change in labware plastics, from the previously used 1 ml round bottom tubes to a 96 well PCR style plate. This is to take advantage of standardized lab modules for heating and mixing. Because we switched to this 96 well PCR style plate, we had to scale down the sample volume and reagent volumes. Additionally, denaturant was previously provided lyophilized in the 1 ml round bottom tubes, so that had to be provided as a bulk reagent to enable this new plate format. The design and implementation of an automated workflow is an iterative process. Since we have established our benchmark data, we can perform a test step with the automated method and compare its results to our manual data. If needed, we can make an adjustment and retest. This approach typically requires a number of cycles before honing in on acceptable automation method performance. Our first automation test data generated will be from a protein digestion sample preparation workflow only. This does not include any protein level cleanup or peptide level cleanup. Here we can see results from the initial assessment of the automated method using protein digestion only. To test this, infliximab and C-reactive protein were spiked into rat plasma to generate a 9-point curve from 1 to 100 micrograms per mil. The two graphs on the right show that while mean accuracy data is encouraging, the precision data, as shown by the percent CV, shows that more optimization is needed. Here is a summary of the experiments performed to identify optimized conditions for our automated digestion protocol. As you can see, troubleshooting each and every aspect of the original method can be overwhelming, tedious, and time-consuming. Experiments 1 through 5 assess benchmarking, liquid handling, and heating. Experiments 6 through 9 assess the performance of a plate sealer and its impact on improvements in the method reproducibility. Following that, changes to plate formats, seal piercing, and deck reconfiguration were tested prior to confirming the final method. Now let's take a look at how good the data is once we get over the hurdles of automated method development. In this proof of concept experiment, we compared data from a manual workflow to our newly designed automated protein digestion workflow using a Hamilton START liquid handler. Analyzing the data for C-reactive protein and infliximab, focusing on the red bars representing automated raw area counts for each of the surrogate peptides normalized to the raw area counts of the manual data, we can see very good comparability, within plus or minus 20%. In addition, the variability of the measurements for both manual and automated digestion have single-digit % RSDs. Following testing automated digestion, the next logical step is to test automated protein digestion combined with automated peptide level cleanup. In this slide, we present data on the biotherapeutic Trastuzumab acquired on a Waters Xevo TQS coupled with automated digestion and solid phase extraction on the Hamilton STAR liquid handling platform. With this method, we can reach a 100 nanogram per ml limit of quantification without the need for affinity purification. Comparing a diversity of tryptic peptides, we find this method to be very robust when compared to the manual workflow. This automated demonstration of the surrogate peptide workflow enables reproducible, precise protein quantification directly from plasma or serum. In addition to digestion and peptide level cleanup, affinity purification can also be automated. Let's take a look at the impact of affinity purification on the sensitivity of our assay. To compare manual versus automated affinity capture, we performed affinity capture using an anti-human antibody on magnetic beads and purified Etanercepe, Infliximab, and Trastuzumab from rat plasma. Digestion was performed manually using the ProteinWorks AutoExpress Low 5 Digest Kit. If we focus on the red bars of the graph, representing automated raw area counts of each peptide normalized to manual raw area counts, we see excellent comparability, within plus or minus 6%. If we take a look at the reproducibility of the data, we can see that the variability of the data is within the specified acceptance criteria of the assay. More often, hybrid LC-MS workflows are employed to achieve greater specificity and sensitivity. It is desirable to automate both affinity capture and digestion. Let's take a look at what that looks like now. Affinity capture and digestion of Etanercepe were performed together using an anti-human antibody on magnetic beads and the ProteinWorks AutoExpress Low 5 Digest Kit, fully automated on the Hamilton STAR. From 50 microliters of plasma, this assay achieved over 4 orders of linear dynamic range, single-digit CVs, and accuracies between 96 and 107% of QCs. Robustness of the automated sample preparation and LC-MS analysis workflow is a key measure of quantitative performance of the overall system. In this graph, we plot the % RSD across injection number for 2 peptides from the Trastuzumab internal standard spiked before capture and digestion. % RSDs were less than 10% across the analytical run. Now that we've taken a look at the performance of each of the steps of the surrogate peptide sample preparation workflow when automated on the liquid handling platform, let's take a look at the final configuration for a standardized, automated, large molecule bioanalysis system. Here is a look at the final deck layout used for the application of digestion and solid phase extraction demonstrated here today. As you can see, numerous on-deck accessories are required for automating this workflow, including heaters, a shaker, tip locations, reagent reservoirs, vacuum manifold location, a plate sealer, and more. This deck layout can be applied to the Hamilton STARlet, STAR, and STAR Plus systems for full automation of protein bioanalysis. Here is a summary list of deck accessories required for automated protein digestion and solid phase extraction. It should be noted that custom parts available from Hamilton are required for this method's particular needs. A piercing module was created to ensure we could accurately pierce through foil seals. Additionally, a dark box was created to perform the light-sensitive alkylation reaction on deck to avoid manual intervention. The protocol can be executed through the workflow selection window with various options for digestion and solid phase extraction peptide level cleanup. This makes it accessible to non-programmers. Additionally, you can input starting sample volume, the number of samples that you'd like to process prior to proceeding through the method. This makes it flexible to accommodate various numbers of starting samples. To summarize, automating sample preparation for large molecule bioanalysis can offer many benefits. It can simplify multi-step protocols and increase capacity and laboratory efficiency. Off-the-shelf deployment is afforded by standardized protein digestion kits designed for automation with the appropriate labware and consumables. Commercially available liquid handlers, sample preparation accessories, and validated scripts remove barriers to adoption of automation technology. Method robustness and assay comparability can be demonstrated through comparison to manual methods. Thank you for watching this module on developing an automated platform for standardized large molecule bioanalysis sample preparation.